Hello, everyone. Are you excited for another pre-calculus lesson? I hope so. It's going to be fantastic. Alrighty then. So, today we got some new stuff going on. I've got a nice donut here. I'm going to eat that later. All right, I'll put that off to the side. The basic gist today, we're going to start a new topic. It's called power functions, one of my favorite things in the entire world. I've got some graph paper here, but power functions you've already seen before. And yeah, so there we go. So power functions. They're of the form f of x equals k times x to the p, where p is a power, k is a constant. All right, so constant, exponent. Now, these are not exponential functions, so that's the first thing we're going to come to grips with here. They're not exponentials. Remember, exponentials look like this. What is the huge, huge difference here? The input is the exponent for exponentials. Here, the input is the base. The power remains the same. Here, the power changes because that is the input variable. Okay? So power functions, kx to the p, and that's kind of what we're going to deal with. But first, we're going to do some easy problems as a little refresher. Okay? And the first couple are actually going to be, they look more like rational functions instead. All right, so let's do a couple problems of the day. I can push this lesson out to you if you'd like to have blank copies or filled in copies. It doesn't really matter to me. This is going to be basically the lesson anyway. So you could just kind of watch the video however many times you need to. Another thing to be said for pre-calc stuff, you can get whatever grade you so desire. It's going to be whatever effort you want to put in. So watch the videos a number of times, answer the problems. If you don't get the grade you want, do the problems again. All right, many of you have not been shy for emailing me, which is totally fine. I will not do specific problems on Con because they're all different for each individual person, as you already know. I will do just a general one that's on Con and hope that you could follow the exact same rationale for each problem. So changing a number shouldn't really be that different. Changing a function shouldn't really be that different. It's the same process. Desmos.com, also a great resource. Let's revisit that since I don't think many of you are using it, especially if you forgot your graphing calculator like I did. All right, Desmos, you click on it, sign in with Google if you so desire, or just go to Start Graphing. All right, and we get all sorts of cool stuff. I would use this as your tool because it's going to give you all of the answers to anything that's asking you to graph, which, you know, it's kind of like legal cheating. Alrighty? So, let's just do these limit problems. We haven't done a limit problem in a long time. Remember, the limit is saying what the function itself, so in this first case, oops, it's a minus 2. The limit is saying what is f of x doing as x goes to 3. So if you wanted to read this out, it would mean as x approaches 3, what is f of x doing? What's happening to f of x? Okay, so in this particular case, it's going to be super duper easy. Well, as x goes to 3, what's happening to that function right there? Well, what we're going to do is we're going to substitute 3 in, and we're going to do the easiest math known to mankind. We're going to get back 6. Now, this is a continuous function at x equals 3. That's a little bit above our pay grade for right now, but we did talk about it in the very beginning of the year. What we're saying is that the function doesn't have any holes, breaks, jumps, gaps at x equals 3. So when x equals 3, f of x equals 6. And if you did put this into Desmos, you would see that the ordered pair 3, 6 exists. So the limit is equal to the function value. Okay? Now I'm going to show you that on Desmos real quick. This has been a little bit, like I said, in terms of limits, discussion of limits. So here we go. We got x plus 3. Look how nice and fun this is. We're going to do divided by, and it's going to give us a fraction just how we like it, which is great. So there's our function right there. I want to know what's going on at 3. Well, let's see. At 3, which is right smack dab in the middle, I'm going to go up here, and you're going to see the ordered pair 3, 6 on the graph. Now, what do I mean by continuous? There is no whole breaks or jumps. We can see that all the action for that one is happening at x equals 2. Okay, so that's our first limit problem. Super duper easy. I'm going to go through this next one. All right. So again, same idea. How does this relate to power functions? We're not quite there yet. But the basic gist is, for example, number 2, the limit as x goes to infinity of 5x to the third plus 3x squared all over 7x cubed minus 2x plus 3. All right, there's a super easy way to do this problem. We have cubics dominating the numerator. We have a cubic dominating the denominator. So the answer to this problem is really, I'm going to not use the exact equal signs because it's not exactly equal to, but it's pretty much this function is behaving like its lead term in the numerator and its lead term in the denominator. And if we do that, the x cubes will cancel out, and I'm going to get 5/7. Now, this is what every math teacher has complained about for every year of their lives that they've taught. Please, dear God, it's not like we're just crossing out all of this other junk and we're just crossing out the x cubes. It may seem that way, but I'm going to show you the algebraic version of this one time so that hopefully it makes sense and you believe in the fact that this is not magic. Remember, math, antithesis of magic. Okay? So what I'm going to do to change the appearance of any function ever, and I haven't drawn one of these in a long time, so I'm actually pretty stoked. What I'm going to do to change the appearance of anything is I'm going to multiply by 1. Okay. And why am I multiplying by 1? We already know this because we've been in this class since September. If I multiply stuff by 1, it will change the appearance without actually changing the value, which is what we're after. If I multiply by 1, what happens? I'm going to distribute this through, and I'm going to get the limit as x goes to infinity of, well, let's see, that's just 5. And then if I distribute 1 over x cubed times 3x squared, 2 of the x's in the numerator will cancel with 2 of the x's in the denominator, and I'll be left with 3 over x. In the denominator, I'm going to be left with a 7 minus 2 over x squared. If the distribution is confusing you on this, that is on you. I am distributing. This is pre-calc. There is no, I'm not going to go slow in distributing one factor. Okay? Now, we're going to actually do the limit. Well, as x goes to infinity, what happens to a fraction whose denominator gets bigger and bigger and bigger and bigger and bigger? That goes to 0. That goes to 0. That goes to 0. So what are you left with? 5 plus pretty much 0. So 5-ish. All over 7 minus 0 plus 0. So pretty much 7-ish. Now I'm going to use the squiggly equal signs for this particular problem because it is tending to 5/7. It is not equaling exactly 5/7 at every single journey on your way to infinity. But as you approach infinity, all of these y values are tending to 5/7. You can get as close as you want to 5/7, and that's the answer to the limits for number 2. Number 3, similar idea. It's another limit to infinity. This time the cubic is in the denominator and there's a quadratic in the numerator. How is that going to affect things? Well, we can do ratio of leading terms, or I can show you this algebra one more time. So that's what I'm going to do. So here we go. I realize the date is wrong as well. I'm just using this from last year. It gives us something to play with at least. All right, so here is the new function. Again, you can put this right in your Desmos or your graphing calculator. I'm liking Desmos better than the graphing calculator these days, to be honest. All right, so here's the deal. We got this scenario. That's what we're looking at. If I want to do ratio of leading terms, I got to feel like this. This is a good analogy for Bill Gates' bank account. If Bill Gates has an ungodly amount of money squared times 4, it is a very, very, very large number. If he adds $5 to that very large sum of money, It's like me asking you, hey, I have $3 trillion. What happens if I add $5 to that? All right, is that $5 making or breaking my net worth? No, it's not. So the ratio of leading terms, I want to do it that way first since it's very easy. It is not magic. It is not just crossing out stuff. Squiggly equal signs, because we're saying that this function right here is long-term. So as x gets very big, long-term behaving like this. Now we know that value is actually extremely easy.
Here's your reminder. Topics Google Meet.
Thank you, Alexa. So if I do this, I'm going to have negative 2 over 3x.
Here's your reminder.
Alexa, stop. As x gets super duper big, negative 2 over infinity will give us 0. And that is the ratio of leading terms approach. That is super easy. And then I'm going to stop this for right now. Pause this recording real quick, because I have a Google Class Meet. All right, we're back. I'm going to do problem number 3 here. Let's see. Different limit. X goes to infinity. 5 minus 4x squared. No, we already did that one. Sorry. The fourth one. Let's see. We have the limit as x goes to radical 3 of x squared minus 3 all over x minus radical 3, which I really like this problem because it undoes some lies that were taught to you by other math teachers. They said there's only such thing as a difference of perfect squares if it was a perfect square minus another perfect square, and they said 3 is not a perfect square. Well, it is. Any number is a perfect square. It's radical that number times radical that same number. So radical 3 times radical 3 is 3. So this actually factors. And right here we get this awesome cancellation to 1. And then as x goes to radical 3 plus radical 3 is 2 radical 3. So those are the answers to all of the limits. And we're going to move on to the idea of a power function. So that's what you're looking at here on my screen, which is pretty cool. Also, I forgot that the document cam wasn't on right there, so you can get a good look at that. I did factor the x squared minus 3 into the quantity x minus 3, quantity x plus 3, divided by x minus radical 3. Those cancel out. I'm left with asking myself, what happens as x approaches radical 3? Well, if we get super close to radical 3, add it to itself, I have 2 of them. Well, why couldn't I just plug in radical 3 in the first place? And that's because I would get radical 3 squared, which is 3, minus 3 is 0. Radical 3 minus radical 3 is also 0, and the dreaded 0 over 0 case is equal to, who knows? Could be equal 1, could equal negative 1, could be undefined, could be infinity. So that's called the indeterminable case. Alrighty? So anyway, just some practice with limits. We haven't talked about them in a while. We're going to go back to talking about what a power function is. That's going right here. All right, take a look at that. Give it a quick little read on your screen. Again, I can fire this out to you, filled in or not filled in, whatever you prefer. I think not filled in is what I will do, so you can just watch the video. All right, what can you tell me about the following graphs in relation to g of x equals x squared? All right, well, this guy right here, 3g of x. So these are examples from the notes. Y equals 3 times g of x. And they're saying that g of x is equal to x squared. Well, we know this guy is g of x vertically stretched by a factor of 3. And if you don't know that, bury that deep within inside you. Okay? That's the only thing we've talked about for the entire year. The other example is this guy, f of x. And that's going to be negative 2g of x minus 2 plus 3. And we're going to go back and figure out how does f of x relate to this guy right here. This is our parent, our original function, our OG, if you will. So this guy, clearly, simple, reflected over the x-axis. Not only that, it's vertically stretched by 2. By a factor of 2. Right 3. Up 3. Or sorry, right 2. Up 3. Okay, so some basic stuff that we've been working on. That should be pretty familiar for everybody. So next slide in the old notes here, we have to have our basic vocab. I am not gonna, that's already printed out for you too. I can send that along. But the idea of increasing, the graph moves up as we go left to right. So this graph is increasing from 0 to infinity. This graph is decreasing from negative infinity to 0. This guy increasing from negative infinity to 2, decreasing from 2 to infinity. Concavity, the rate of change of your rate of change is either increasing or decreasing. So the idea is, well, pretty easy. Is this guy smiling at you or is it frowning? So if I drew little line segments in here, the line segments would be increasing in slope. Therefore, the graph is concave up. Line segments, remember, would be the average rate of change. Your average rate of change is getting bigger. Your average rate of change is increasing. Here, your average rate of change is decreasing. The slopes are becoming less steep as you go from left to right and then becoming negative. Remember, negative number smaller than a positive number. So that is that. And then, yeah, here's what Mrs. Thompson had on there 100 years ago. Smiley face or frowny face, and I like that because if you're 5 years old or less, you can think of it like this. Again, I'll send this along so you can read it. What we're going to do now is we're going to go through and let's see what I got to do. I'm going to go through and pull up this guy right here. I'm going to send this along as well, and you guys are going to work on it. And I think it's really cool because it's a little bit of exploratory activity. All right, so you're going to give a power function. The first one, y equals x. Let's see, sketch it. Everybody should be able to sketch that thing. All righty. Symmetry. What kind of symmetry does it have? Is it symmetric about the y-axis, aka an even function? Is it symmetric about the origin, aka an odd function? Is it symmetric about the x-axis? Does it have any other kind of symmetry? When does it increase? When does it decrease? When is it concave up? When is it concave down? What are the intercepts? All basic questions from your 9th grade year in algebra. And then this one's a little bit more heady though. When or if are there asymptotes? So the first one is super dull, but we can kind of go through it. Make sure you're understanding what I'm putting down. Which, please, I hope you are, since it is the line y equals x. All right, here we go. So if you're going to fill in that chart, flip-flop back and forth, but it says your first function, type of function is f of x equals x. All right, it asks for a description of the shape. We already know what that looks like, or at least we should. It is that line right there. It asks for when it's increasing or decreasing. So this graph is increasing for all x. All right, concave up or concave down. There is no concavity. It's a line. Concavity, or line, has a constant rate of change. And concavity, by definition, is when your rate of change changes. And if the line is a constant rate of change, it does not. The rate of change does not change, it remains constant. Okay, so now we're going to go here. Symmetry, there is no symmetry. And then let's see, no concavity, increasing, decreasing, we already took care of. And then we want the intercepts and asymptotes. All right, intercepts and asymptotes. Y and x intercept are both the same. Both 0, 0. And last but not least, there are certainly no asymptotes. So that's how you do one of these. Now again, the directions on the sheet that will be pushed out to you, I will show you these directions. They say, correctly fill in the chart and use a pencil. They don't say that you can't use your graphing calculator or Desmos. So please do that if you have zero clue of what you're doing. All right? I'm going to go to a more interesting one. We'll do y equals 1 over x. And we'll kind of fill in these charts, and then I'm going to end the video and let you guys play. Alrighty? So here we go. We're going 1 over x. So that's going to change things. You have seen this graph last year in your other courses. So 1 over x has a great shape to it. This is my marathon math dancing. So hyperbola looks like this. Okay, pretty cool stuff there. Now we're going to get some easy stuff going here. All right, this graph is decreasing, or actually symmetry, I think was the next one. Symmetry about the origin. So if you want to get bonus points for me, that is what was called an odd function. All right, increasing, decreasing. This graph is decreasing on the interval from negative infinity all the way to 0. It is also decreasing on the interval from 0 to positive infinity. Now, why don't I just write all reals? Well, I'm not writing that because we can see from the graph here, or whatever graphing program you're doing, this thing is not defined at x equals 0. Algebraically speaking, if I'm looking right here, if x is 0, 1 divided by 0 is undefined, hence the reasons that we have this giant gap. Okay? Next up, what are we looking for here? We've got, let's see, sketch, symmetry, increasing, decreasing, concavity. Okay, concavity is a good one. And then intercepts. So concavity, pretty cool. This thing is frowning, and then it's smiling. So concave down from negative infinity to 0. It's concave up from 0 to positive infinity. Okay, now what I mean by that is your rate of change is decreasing as we move from left to right, hence the concave down. And right here, the rate of change is going from negative slopes to less negative slopes to less steep negative slopes. So it is increasing, hence concave up. Intercepts. If I'm looking at the intercepts, here's our x, here's our y, here's our graph. We can pretty much easily see that there are no intercepts. So you can write NA in your chart if you so desire. And then last but not least, asymptotes. All right. Okay, so asymptotes are where the limit comes in. The vertical asymptote is going to be pretty easy. It is when you're dividing by 0. So 1 divided by 0 is undefined. And that is the equation of your vertical asymptote. X equals 0. Horizontal asymptote is a better question. We're asking ourselves what happens as you go to, well, first plus infinity and then negative infinity. Well, this is really easy. As you follow the graph going, if x gets super duper big, the y values tend to get really, 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 really small. algebraically speaking, what's 1 divided by 10 trillion? Super duper small. How small? 0. So your horizontal asymptote equation is y equals 0. Same thing works if you go to negative infinity. If I follow leftward, so again, I'm going out to negative 10 trillion as a little stopping point for on our way to a negative infinity. What is 1 divided by negative 10 trillion? Well, something that is extraordinarily small. So that's the idea of this graph hugging the horizontal asymptote. Okay? And that's a really good one to do. And signing off for right now, I'm going to eat this delicious donut. And yeah, here we go.
Hey, this is my donut.
It's not a donut.
Oh my God, it's fake!
Give me my donut.
Whatever, man.